Hello and welcome to York Observatory YouTube TeleTube, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. I'll be one of your hosts this evening, Arfa, and I'm joined by Connor and Laura, and of course, our guest this evening, Mani Mehdipoor. Broadcasting live from the LNI Carswell Observatory located at York University in Toronto, Ontario, Canada. York YouTube broadcast every Wednesday night at 7:30 local Toronto time. For any questions or comments you have of our past shows, or if you have any suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Twitter or Instagram with the handle at York Observatory and Facebook at Alan I. Carswell Observatory. I'm Arfa and I'm here with Christina, June, and Matt. Tonight we've got a great presentation about star cluster exploration with the York Observatory 1 meter telescope by observer member Mani Mehdipoor. But first, let's look at what the sky tonight holds. We can expect to see Venus until 10:30 p.m. tonight and Mars till around 10:11 p.m. and Saturn and Jupiter rise around midnight. Neptune and Uranus are not visible to the naked eye but do rise at 1 a.m. and 3 a.m. respectively. Mercury will make a late entrance, rising at 5 a.m. with the Sun. On the 27th, the Moon will pass 5 degrees below Saturn.
Oh, that's really interesting. Thanks, Arva. This is Dr. Hyde, just saying we're very much looking forward to seeing some of these, perhaps even live imaging through the 1 meter telescope. Obviously, as Arfa has mentioned, we have all kinds of great things up in the sky, but at the moment, one of those things is still the sun. Now, I have the honor to introduce our speaker tonight. I'm very, very excited to be able to introduce Mani Mehdipoor, a co-op student from the general Toronto area, and in particular the Stephen Lewis Secondary School, who's been working with our observatory, with the LNI Carswell Observatory, I should say, all summer. So Manny has been our co-op student and has done a wonderful investigation into open and globular clusters using the 1 meter telescope here on campus. And I'm going to let him tell you all about that. But as an introduction, I'd just like to congratulate Manny for an excellent summer project. And of course, in showing such an enthusiastic spirit of exploration, which I think you will agree comes across very, very well in the talk here today. So Manny has not only looked at these astronomical objects, but has also done wonderful work helping our observatory archive and making some lovely mosaics, actually, which I think we might just catch a glimpse of. So, without any further ado, or hopefully any further audio issues, I am going to leave it to our fantastic speaker to tell you all the rest. So, take it away, Manny.
Thank you, Professor Hyde, for that great introduction. Hello, everyone, and thank you for joining our TeleTube tonight. Today, I would like to share with you my research on globular clusters, especially focusing on a particular one commonly called M3 or Mesder 3. I am going to try my best to walk you through the classification of star clusters, the birth of star clusters, the importance in astronomy, and also their eventual fate. I will talk specifically about the M3 cluster and how it sits relative to other globular clusters. Tonight, we are also fortunate enough to see some fantastic astronomical images taken from the M3 cluster and the Beehive cluster using the 1 meter telescope here at York University. If you are curious, the M3 projection on the right of this slide was made by me during this year's partial solar eclipse. I used the pinhole projection technique posted by NASA to create this image, and many other cool patterns. The solar eclipse was part of an event by LNI Carswell Observatory, and if you want to see more fantastic eclipse pictures that we took at 5:35 a.m. on June 10th around the Toronto area, you can check out our special TeleTube episode on our official YouTube account. Also, check out NASA's website to learn how to make a pinhole camera yourself, and maybe you can try to do something similar in the next partial eclipse that happens in the Toronto area on October 14th, 2023. I am a co-op student at LNI Carswell Observatory, and during my time here, I got to try many different astronomical techniques and applications. I am planning to pursue physics in the future, and I am particularly interested in particle physics. In this TeleTube, we will see many of the visuals that I have created during my time at the York University. I created most of my graphs using TopCap, which is an astronomical data analysis software that is pretty easy to use for beginners. I have also used Python to create a very cool 3D graph of the location of globular clusters in the Milky Way. I use Matplotlib and NumPy libraries in Python to create these graphs. Before my co-op experience, I had never used Python, but with the support of Professor Hyde and the tutorials she sent me, I had a lot of fun learning this new programming language that is very useful for data analysis. For my image reduction and my image editing, I use many different software such as Stereo, Deep Sky Stacker, and GIMP. I find Serial very easy to use for simple data reduction. And they had a very easy to follow tutorial on their website, which I used to reduce the beautiful CCD pictures that I took with Arfa and Quentin into these final images. I then combined the red, green, blue filters of the images with GIMP, and I did some final editings in GIMP to bring out some of the features of the clusters. I embedded 3 of these reduced images in my slideshows. We will see one picture of the M3 cluster and 2 pictures of the beautiful M44 cluster. On this slide, we can see the moon mosaic that I have created during my time at the LNI Carswell Observatory. I use a very cool application called Image Composite Editor by Microsoft to combine all of my images into this beautiful mosaic. The application detects the overlap between the images and it automatically arranges the images to a beautiful mosaic. I then used GIMP to do some final editing on my final mosaic. Before I go to my main presentation, I also want to thank Shannon and Gigan for training me through TeleTube and June for his very educational data reduction training. Without further ado, let's get to my main presentation about star clusters. A star cluster is fortunately a pretty self-explanatory name. A star cluster is a collection of stars that are physically close together in space. They are smaller than the galaxies they inhabit but provide very interesting environments. I like to think of them as a family of stars, but unlike families, they only have 2 types, open and globular. We will discuss these 2 types later in the slide, but I want to mention that these 2 types have both different ages, shapes, colors, and their evolutions. Star clusters have been known to us since ancient times. There are several star clusters that can be easily detected with the naked eye. For example, open clusters such as the Pleiades, Hyades, the Beehive, and Coma Brentzises were identified a long time before the invention of telescope. According to Encyclopedia Britannica, some early people even associated the rising of the Pleiades at sunset with the indication of a new year. However, for globular clusters, even for a few such as Omega Centauri and M13 are visible with the naked eye, they were not really studied before the invention of telescope. Star clusters are usually divided into 2 main categories. Open clusters, also formerly called galactic clusters, and globular clusters. Open clusters are usually irregular in shape, hence their name. They can contain anywhere from dozens of stars to thousands of stars, and can be both compactly or loosely arranged, for they tend to usually be less compact than their globular counterparts. Globular open clusters are also always found within the disk of the galaxies. Open clusters are generally blue in color, and since blue stars are hotter, they consume more energy and have shorter lifespans. So we know that open clusters are usually formed from newer second generation stars, meaning they are formed from the remnants of already dead first generation stars. Most open clusters have been around for much less time than our Earth. They only live up to a few 100 million years. However, the massive ones can live up to billions of years. One of the oldest open clusters discovered to date, NGC 6791, is estimated to have an estimated age of 8 billion years. In general, since open clusters are the result of many stars forming from a single cloud of gas, these stars are young, blue, active, and mostly will drift away from their cluster over time. It is thought that quite a lot of these stars end up spread out through the arms of the universe, such as our own Milky Way, and our Sun would once been a member of an open cluster. In fact, some astronomers are actively searching the Milky Way to find other stars that form with our Sun, solar siblings, if you will. In contrast, globular clusters get their name because of their more spherical shape. However, these clusters are also in all other aspects. They contain old and red stars rather than young and blue stars, and they are much more compact. Have very little chance of getting disturbed or broken apart because of their strong gravitational attraction and because they orbit outside the plane of the Milky Way. They are in fact some of the oldest objects in our galaxies. Globular clusters usually contain more stars than open clusters. They can contain anywhere from thousands to even millions of stars. Omega Centauri, one of the largest known globular clusters, contains 10 million individual stars. Globular clusters are usually more densely packed than the open clusters, and they have very bright and massive cores. They are usually found within the halo of the galaxy and orbit the galactic center, instead of being located in the arms of the galaxies like open clusters are. They are formed from first generation red stars, typically red giants and supergiants, which live way longer than bluer stars. Globular clusters are usually extremely old and formed in the beginning, near the beginning of the universe. They usually have ages of above 10 billion years, with our subject, the M3 cluster, having an age of around 11.4 billion years, meaning it was only formed 2.4 billion years after the Big Bang. Some of the Milky Way's globular clusters are even believed to have been originally formed in other dwarf galaxies, and they have been removed from the dwarf galaxies to join the Milky Way. The subject of today's presentation, the M3 cluster, is extremely difficult but not impossible to see with the naked eye in perfect viewing conditions. However, using a simple 10 centimeter telescope or even just a pair of binoculars, you might be able to detect the bright core of the cluster. The M3 star cluster, also less commonly called NGC 5272, is one of the most well-studied globular clusters after M13, and it is very appealing to amateur astronomers. Interestingly, the M3 cluster was the first object in the Messier catalog to be identified by Charles Messier himself. He discovered the cluster in May 3rd, 1764, but unfortunately he misidentified the object as a nebula, and it wasn't until 1784 when William Herschel finally corrected Messier's mistake and identified the object as a star cluster. M3 is visible from the Toronto area for most of the year, and right now it is placed pretty high in the sky. So if you have clear skies this evening, it is a pretty good object to aim at with your binoculars or telescopes. It is believed that the majority of stars are formed in star clusters. Our sun, for instance, was most likely formed in an open cluster 4.6 billion years ago, and then over time it slowly drifted away from its from its open cluster. Just like stars, the lifespan of a star cluster also starts from a giant molecular gas. Once the molecular cloud gets disturbed by a force, it starts to collapse into itself and form areas of extreme density. The gravitational potential energy in these dense regions of the cloud turn into kinetic and thermal energy, and stars eventually begin to form in the densest region. Since usually many stars are formed just from one molecular cloud, these new stars are usually gravitationally bonded to each other at the first. Usually, after the formation of some stars, the remaining cloud is also heated up and blown away from the star cluster. The newly cluster of gravitationally bonded stars move through space almost as a single object, and they orbit the galactic center. However, in most cases, the stars eventually escape the cluster and the cluster disperses into nothing over time. This is very cool done and very good simulation. On the left of the screen simulates how a star cluster could be formed. If you are interested to learn how this simulation was done, or if you just want to know what it shows, or even if you just want to see more cool astronomical related simulations, go check out UK Astrophysical Fluid Facility website at ucaf.ac.uk. The type of a star cluster is determined before the cluster is actually formed. The formation of a star globular cluster is still debated in astronomy, and there are many promising theories that could explain its formation. The mass and density of the molecular cloud likely determines the cluster's type. Globular clusters are some of the first objects that have been formed after the Big Bang. According to an article by University of Oregon, globular clusters are formed from insanely massive molecular clouds. Since these clouds were so massive, they produced more stars, and therefore the star cluster that was formed from them has a stronger gravitational attraction. This stronger gravity has prevented most of the stars from escaping the cluster, and over time, the cluster has shaped into a stable spherical shape. Harvey Richer from University of British Columbia also states that the reason that there are usually no more globular clusters forming today is because there is less free gas available in the universe than there was in the beginning of the universe. Open clusters, on the other hand, are usually formed from much less massive molecular clouds. Unlike their ancient counterparts, open clusters are pretty young and many of them are just beginning to form right now. Many open clusters still have their nebulosities with them. Some very new clusters are even invisible to our light telescopes like the one that we have at the observatory. And we have because of the dust that is blocking them from view. So we have to study them through infrared observing. Since open clusters have a weaker gravitational bond, they usually disperse quickly and they can be easily disturbed by massive objects. On this slide, we can see two of the youngest open and globular clusters. NGC 362, one of the youngest globular clusters, was still formed 10 billion years ago, which is way before the formation of our sun, which is just around 4 billion years ago. However, in contrast, the trapezium cluster, one of the youngest open clusters, is only estimated to have been formed around 300,000 years ago, which puts its birth even ahead of the invention of fire by humans. Even though they might not look as impressive as black holes and nebulas, globular clusters are extremely important to astronomy for a couple of important reasons. One of these reasons is their age. Globular clusters are usually at least 10 billion years old, meaning they were formed no longer than 3.8 billion years after the Big Bang. In biology, biologists study fossils to understand the evolution of life and predict the future of life using the past trends. Globular clusters are pretty similar to fossils in terms of the universe. They are living samples from the first star formations in the universe. By comparing stars in a globular cluster and newly formed stars, astronomers can easily see how the universe has changed over all of these years, and they can start to detect patterns in the evolution of stars. Globular clusters can also help us grow our knowledge of the Big Bang and the early stages of the universe. One thing that can easily be seen from the globular clusters is their very low surface metallicity level. For example, this graph that I have created shows the chemical abundance ratio of all globular clusters in the Harris catalog. The chemical abundance ratio is calculated by taking the average logarithm of the iron to hydrogen ratio of a cluster and subtracting it by the logarithm of the iron to hydrogen ratio of the sun. So a -1 chemical abundance ratio means the cluster has an average 10 times less metallicity than our own sun. The average chemical abundance ratio for all globular clusters in the Harris catalog is -1.3, meaning most globular clusters are 20 times less metallicity, have less metallicity than our own sun. This interesting result is due to the fact that most metals in the universe come from supernova explosions. Since stars in globular clusters are first generation stars and there weren't too many supernova explosions in the beginning of the universe, there is less metallicity on the surface of globular clusters of stars. In laboratory experiments, scientists always try to control as many variables as they can to get reliable results. However, this is very difficult to do so in space, since there are just too many changing variables in space, and that makes it so much harder for scientists to study space objects. Which, when it comes to studying stars, star clusters are usually one of the best places to go. Generally, stars in a star cluster are formed in about the same time from almost identical materials. They can be they are also at the same location in space and have similar external forces acting on them. This is extremely valuable to astronomers since they can easily compare and study stars in the same star cluster and get more reliable results. For example, if an astronomer measures the apparent magnitude of two stars in the same globular cluster and one appears to be twice as bright as the other, the astronomer can confidently assume that the one that appears twice as bright is actually twice as bright. Since they are at the same location, their apparent and absolute magnitude should be about the same. Lastly, these globular clusters are pretty useful at calculating distances in space. Even for calculating distances might seem like an easy thing to do in the day-to-day life, it is actually pretty hard to do accurately in astronomy. One of the best tools for calculating distances are in, intrinsic variable stars. These stars actually change luminosity over time. For instance, they shrink and swell periodically. Intriguingly, for some of the variable stars, the period of these luminosity changes is directly related to the absolute magnitude of the star. Since we know the apparent magnitude and we can calculate the absolute magnitude using the square root law for apparent magnitude, we can easily calculate the distance of the stars with a good degree of accuracy. Globular clusters are home to a lot of variable stars, in particular RR Lyrae variables, also referred to as cluster Cephides. Type of variable stars are also commonly, or this type of variable stars also have very short and frequent periods. As well, they also have well-established period luminosity relationship. So they are great resources to indicate distances in space. These RR Lyrae stars are also common study subjects for studying chemistry and quantum mechanics in older stars. M3 has a pretty interesting discovery. The cluster was the first object in the Messier catalog to be discovered by Charles Messier himself. M3 is also the 75th deep sky object to be ever discovered. Charles Messier was a French astronomer born in 1730, and he's most famous for publishing a catalog of 110 sky objects that are known today as Messier objects. Messier discovered the M3 cluster on May 3rd, 1764. He used a Gregorian telescope with 104 times magnification. However, unfortunately, Messier misidentified the object as a nebula with no stars. This misidentification is probably due to the fact that under the low magnification of the telescopes at the time, the bright core of the M3 would look similar to a nebula. William Herschel, a famous British astronomer, re-observed the object in 1784 using a 20 feet long reflector shown in the right-hand side of this slide. It has 171 times magnification, and he was able to be the first person to correct Messier's mistake and correctly identify the object as a globular cluster. William Henry Smith, a British naval officer and astronomer, revisited the object in 1831, and he gave one of the earliest thorough explanations of the cluster. Later in 1832, William Herschel's son, John Herschel, also observed the object, and he estimated the cluster to have at least 1,000 stars. Today, we know that M3 contains somewhere around 500,000 individual stars. At the LNI Carswell Observatory, we are fortunate enough to have access to a modern 1-meter telescope that can amplify the M3 cluster to a great amount of detail. So we don't have to worry about misidentifying the M3 as a nebula for our images. Only about 250 globular clusters have been identified in the Milky Way so far, and M3 is one of them. The M3 cluster is relatively large compared to other globular clusters. It has a very massive and bright core with a diameter of 1.1 arcminutes, and the total diameter of the cluster is around 180 light years. The cluster is located around the halfway point between the star Arcturus in the Bootes constellation and the star Caroli in Cain's Vanatici constellation. If you are located in the northern hemisphere, the star is pretty visible in the sky between the months of March to May. And like other globular clusters, the M3 is located at the halo of the galaxy. Compared to the other globular clusters, M3 has a pretty central location. In the 3D graph of all globular clusters that I have created using Python and Matplotlib, M3 is colored in red, while the other globular clusters are colored in blue. The semi-transparent blue cylinder is the rough location of the Milky Way's disk. Made thicker, of course, since the actual thickness would be too thin to see clearly in this graph. You can see that most globular clusters are not located within the Milky Way's disk, and they are all located around the halo of the galaxy. The M3 cluster lies 38,800 light years away from the galactic center and 31,600 light years above the plane of the Milky Way. The cluster is also 33,900 years away from us, and that number is pretty accurate thanks to a large number of the variable stars that the cluster has. In its galactic orbit, the cluster is approaching us at an astonishing rate of 147.6 kilometers per second, 164 times the speed of a bullet. It is estimated to be around 11.39 billion years old, and this is such a long time ago. To put it in perspective, it's about 2.5 times the age of our Earth, or 1.4 billion human lifetimes. One of the methods that we can use to estimate the cluster's age is through the color of its stars. Since redder stars last longer, if a cluster has a more red wavelength, we can assume that the cluster is older. The VI index of a cluster is its visual apparent magnitude subtracted by its infrared apparent magnitude. Infrared has a larger wavelength than green, and even comes after visible red in the electromagnetic spectrum. If we keep in mind that smaller apparent magnitude actually means a brighter star, then we can see that a bigger VI index actually means a brighter infrared magnitude compared to the visual magnitude, and therefore the redder the cluster is. Since we know that the redness of a cluster is directly proportional to its age, we can estimate the cluster's age solely based on its VI index. This brilliant graph that was done by a code that was written by June, one of the students at York University, shows the wavelength sensitivity of different CCD filters that we use here at York University. You can see how different each filter is and how the ranges and peaks for each filter is different and how some filters overlap at certain points. It is very important for us to keep all of this in mind when we are calculating anything based on the wavelength of colors. I also have graphed the VI indices for all globular clusters in the Harris catalog, and if we look at the M3 cluster with its VI index of 0.93, we can see that it lies somewhere near the average. However, if we actually calculate the mean and median for VI indices of all globular clusters in the Harris catalog, we get 1.33 for mean and 1.22 for median. This means that the M3 cluster is relatively bluer than other globular clusters, and it is probably relatively younger than other globular clusters. The metallosity of a star cluster is also another way to determine its age, even though it is less accurate than the color indices. Since the universe had less metal in the beginning, we know that the clusters that are less metal rich have lower ages. M3 is the prototype for Ostrov type 1 cluster, which indicates that the cluster has a relatively metal rich compared to other globular clusters, which means it is not that metal rich. The M3 cluster is huge, having more than 500,000 stars. As we talked about, most of its stars are old and red stars. Looking at the picture of the M3 cluster that we took using the 1-meter telescope at York University, we can see the redness of the stars pretty obviously. Also, looking at its color magnitude diagram, which is practically the same as an HR diagram, we can see that it clusters breakaway point. This is the point where the cluster starts is branching away from the main sequence and goes into giant branches. A star can only remain in the main sequence as long as it is turning hydrogen into helium. And we can see for the big stars in most globular clusters are either dead or red giants. The color of these stars can also tell us about their temperature. The red stars have shorter wavelengths and therefore they consume less energy and are cooler. In practice, the color index of a star cluster should give us enough information to estimate its temperature pretty accurately. If we consider stars as black bodies and we use the Blastros formula, we can get a good estimate of a cluster's temperature using its BV index. I used the BV index of 0.69 for M3 and got an estimated temperature of 5600 Kelvin for an average star in the M3 cluster. This is pretty accurate considering that an average star in the M3 cluster is actually around 36,000 to 68,000 kelvins hot. We can estimate an average star type of the M3 cluster using our calculated average. If we do that, we get a G-type star for an average star in the M3 cluster. M3 is also home to some very interesting stars. Blue stragglers are some of the stars that have passed the breakaway point of a cluster. These stars are not supposed to exist. They should have been burned out of field by now and be dead. However, these stars still do exist, and M3 hosts an unusually large amount of them. These stars are still not too well known and they are still being studied, but they probably form from stellar collisions. Star collisions are actually pretty rare in space. There is so much empty space compared to the space that stars take up, so chances of two stars colliding with each other is pretty rare. However, globular clusters have so many stars in a very dense area that the best chance of a star collision is inside one of them. These collisions can happen in two different ways. Head-to-head collisions, which is when two small mass stars collide with each other, or a vampire model collision, which is when a lower mass star drains into a larger companion. These two collisions results in two different blue straggler formations, which are demonstrated in this very cool diagram by NASA and ESA. When these two stars collide, we can see that they share fuel and energy and become massive blue stars, releasing large amounts of energy into their globular cluster. And these odd group of stars are the ones that we can see as labeled as blue stragglers in the image on the right hand side of the screen. Another fantastic feature of the M3 cluster is its variable stars. The cluster has a large amount of variable stars among compared to other globular clusters. In 1889, Edward Charles, an American physicist and astronomer, became the first person to ever discover a variable star inside M3. Solon Irving Bailey, another American astronomer, discovered an astonishing amount of variable stars in the cluster. He discovered 225 individual variable stars in M3. Since then, more and more variable stars have been discovered in the M3 cluster. The total number of variable stars discovered to date total at 274. And this list is likely about to expand because of the future exploration of variable stars. This abundance of variable stars has made M3 a very interesting target for professional astronomers. Variable stars are very important to stellar research as the luminosity periods can teach us about distances and how stars work and evolve. At least 170 of the variable stars inside the M3 are RR Lyrae variables. And as we said, these RR Lyrae variables are pretty useful at finding distances in space. And because of them, we can get a pretty good accurate estimate of the M3's distance and also the objects nearby it. There are several ways a star cluster could die. The most common way for an open cluster to die is through dispersion. When a star cluster forms, all of its individual stars also have their own random velocities, which makes them move around the cluster randomly. However, because of gravity, the cluster is bonded together as one object, and they have an overall velocity relative to the galaxy and move in the galactic orbit. However, as more each cluster has escape velocity. And the escape velocity is the velocity which a star needs to reach in order for it to escape the cluster's gravity. Over time, the random velocity of some of the stars in the outer edge of the cluster increase, and some might reach the escape velocity of the cluster. When that happens, stars fly out of the cluster and move away from the gravitational bond. This reduces the size of the cluster and therefore its mass, and therefore the gravitational bonding of the star cluster will be less. So the escape velocity will also be lower. So more stars can escape the cluster, and therefore the cycle will repeat. The gravity will be lower, and then the escape velocity. Over time, stars will reach a new escape velocity. Over time, this cycle will repeat until there is no more stars left in the cluster, and this cluster will cease to exist. This is likely to happen to our own sun as well. It was born in an open cluster, and it eventually gained enough velocity to escape its own cluster and move away into empty space into the position that it is at right now. Another possible way for an open cluster to die is for all of its stars to run out of energy. This usually takes much longer time than dispersion, so it is almost never how an open cluster dies. However, in most cases, it is a combination of star deaths and star escapes that make an open cluster disappear. Globular clusters are a bit more hardy. We can see that globular clusters are living as at 10 billion years and older, and we know that it would take much more for them to die. Similar to open clusters, globular clusters can also die from dispersion or star deaths, but these two will take much more longer for a globular cluster. Globular clusters are much more massive than open clusters. Globular clusters have tens of thousands of stars, while open clusters only have a few hundred. This means that globular clusters have a higher escape velocity, and therefore it may take much more energy and work for a star to escape a globular cluster, and that will take a much more longer time to achieve. This makes them relatively stable over a very long period of time. Stars in globular clusters are also red stars, meaning they run out of fuel very late and they run very efficiently. so they can last for tens of billions of years before dying. These two factors combined make globular clusters last for so long. So we shouldn't expect the M3 cluster to die in the next few 100 million years or so. Some other ways a cluster could die is through streaming out of existence or colliding with other other clusters in general. When a cluster passes through or close to a massive object like a molecular cloud, a dwarf galaxy, or just another cluster, its stars will be affected by the gravity of the object and they will start to move out of their shapes. They will start forming a stream behind the cluster. If this streaming effect is strong enough, it will make the cluster unstable and it will let all of the stars escape the cluster's gravity. This is one way for a globular cluster to miss its end. Another way for a globular cluster to die is through collision with other clusters. Star cluster collisions are not as rare as you might think. Hubble has discovered an area that spent hundreds of parsecs in Antony Galaxy, where some globular clusters will eventually collide and merge into a huge globular cluster, and this region is being called the cluster of clusters. All of the clusters that are merging together have different ages and metallicities. So once they merge into a big cluster, they will have the final cluster will be a huge multi-metallic cluster with a bunch of different star types. That's it, everyone. I hope you found this presentation about star clusters interesting. Next time you have clear skies and a pair of binoculars or telescopes, make sure to spot the M3 cluster. And even if you don't have telescopes or clear skies, make sure to try to aim for other objects. The M13 is pretty visible even with the naked eye. And enjoy looking at the pulses of our sky.
Thank you very much, Manny. That was a wonderful talk on all kinds of great things. Now I think it's about time to try to go live over to the 1 meter telescope and see what we can see uh, tonight. So let me just connect over here. And it looks like we're about to capture the screen. And there we go. You are now viewing the direct live feed from the 1 meter telescope. Yep, we're going to look at a few different things up tonight. So I'll just take any guesses in chat. Does anyone want to guess what we might be looking at only 8 p.m. that looks so nice? And take a couple guesses in chat. Let's see if anybody has a guess to give here. Any guesses from our co-hosts? Anybody want to give a try to say what they think, what object they think we might be looking at? And I think a few people know.
Maybe Mars.
Maybe Mars. That is a good guess, Matt. So that is Matt with Mars. You'll note though, that's a really good guess, but this doesn't quite look red. So we're not getting a lot of red color. Anyone else want to go?
What about Venus? I think it's Venus.
Yes, it is. So Arfa, our host for tonight with the win, this is the planet Venus. And you'll note it doesn't quite look completely round. I don't think it's in a full phase. Now we have a comment from Joshua in chat on YouTube, actually. Venus is, very, very bright. So yes, this is one of the reasons why we are pointed at it right now. Venus being a very, very bright planet means that we can see it even when the sun is technically still up. So I'm just going to pull up, I'm just going to steal the screen here for a second and pull up our 1 meter plane wave interface, which is how we guide the 1 meter telescope, or how I should say Connor and Lore are guiding the 1 meter telescope. And you can see we have this view of the sky, and that yellow circle down in the west here is the sun. So the sun is still technically up, and Venus following it down, um, is bright enough that we can actually just make it out. So about Venus, well, gosh, there's been a lot of Venus in the news just this last year. They thought they might have found some forms of life in the clouds, and now maybe not. But it's always been a planet that has, like Mars, sparked everyone's imagination. So let's go ahead and throw it open for a Venus fun fact. Anybody want to go on the Venus? I think Arfa, you had a little bit of Venus info.
Sure. One of the most popular facts for Venus is that a day on Venus is actually longer than a year. And although it's not as close as to the planet Mercury is to Sun, but it's still hotter than Mercury.
Those are very good facts. And actually, those I think are some of the favorite facts for a lot of students beginning off studying astronomy. How is Venus hotter than Mercury, even though it's farther from the sun? Well, it's thick, cloudy atmosphere. And this is some very thick, acidic, sulfuric acid clouds, which would, melt and squish you. The pressure on Venus is enough to turn a standard human into roughly the size of a tuna fish can, and not one of the big ones. So this planet is actually, although it is the same, pretty much the same mass as Earth, it's quite different on the surface. And let's see here, we've also got a phase for Venus coming in from June over on YouTube. June, do you want to try giving that information directly? Is your audio working? Well, looks like maybe not. This is unfortunately an evening of audio problems, but it looks like the phase is apparently 0.91. So 0.91 being almost full Venus, and that's quite interesting because the moon is also getting full at the moment. So we've got some interesting phases on planets as well as our moon. So you do need a telescope to see
Yeah,
the moon on
I'll
the
try it
Venus.
out.
Go ahead.
Apparently the phase is about 0.91 or 91%, as we can see here. And it's almost a magnitude of -4. That's fairly bright. It's brighter than any of the stars in the night sky. Yeah, it's also apparently at a distance of 1.53 astronomical units, where the astronomical unit is the average distance between the Earth and the Sun, and that's 1.53 times 150 million kilometers. -4.
All right, it looks like we've got that coming through eventually. So we did get June in, so that is great. A little bit of strange audio problems, but here we go. Yes, 150 million kilometers, 1.53 AU away. So that's the average distance between the Earth and the Sun is 1 AU. Um, All right. So Venus, very nice tonight. Very bright. As you can see, Connor and Laura have adjusted the telescope settings here to try to bring out Venus as best we can. If we try to go and make it a little bit bigger, I think we're probably going to end up making it just a smidge blurry as well. But we'll try to zoom in a little bit more. And you can see that it's almost full, so you can get a good idea of the phase, but it's not a complete circle. So if it was a full phase, a completely full Venus, then of course we'd be able to see the disk completely. And 0.91 is just, we've got a little bit of a, I don't know, gibbous, I suppose. I actually forget if that's used for Venus or not. So let me try going back to the default colors here. And you can see a little bit more how the atmosphere is coming in on Venus. This is, of course, live from the 1 meter telescope. Now we have a few other targets which we might be able to get to tonight, so not too many because of course we're still limited by the sun, but Arcturus is our next target. So I'm going to have our telescope operators, Connor and Laure, can you please move to Arcturus and also very carefully go out and move the dome? Let's see, and you can see them doing it here. And this is the 1 meter telescope zipping across the sky. And you can see that's the control screen now. It's moving across away from the sun towards the star Arcturus. Now they're going to be moving the dome as well so that the dome will line up with Arcturus and it will be visible. And while they're getting the dome into position, let's go ahead and talk a little bit about Arcturus. So who's got their favorite Arcturus fact? I think Arfa, you had one for this as well, didn't you?
Yep, it's me. So basically, Arcturus is an orange giant star, and it's actually 26 times the size of the sun. And the best fact about for this one, my favorite, is that it's the fourth brightest star up in the sky. So, like, if you guys want to see it with your naked eye, you can easily point it out towards this star, and it's one of my favorite stars actually up in the sky.
That's actually wonderful. Arcturus is a really good star for all kinds of things. It is, as you say, a nice and bright star. It's fourth brightest in the sky, so it's a good one to point at. It is also quite nice for stargazing. So if you are ever out stargazing, even if you just have a planisphere, you might be trying to find your way around the sky, and Arcturus is commonly used with the Big Dipper constellation. And I'll just pull up our plane wave interface for the 1 meter here to show you. If you've got the Big Dipper constellation, you can kind of make out that shape, follow the handle down, and if you're following the curve of the handle, you can say arc to Arcturus, and if you follow that curve straight down, you actually do land on Arcturus. Now, Matt, you've also got a fun fact, and it looks like we have the star in the field. Here it is shining quite well. We're able to get a really good view on this. So thanks, Connor and Laura, for bringing this up for us. It looks absolutely lovely. I get an impression there's just a little color here. So Matt, go ahead.
Yes, thank you so much, Professor Hyde. One interesting fact I was amazed by it when I read it about Arcturus was that indeed it's really bright. It's so bright that as a matter of fact, scientists used it to open the World Fair in 1933 in Chicago. So what they did is they pointed their telescopes at the light coming from the star, and used several photoelectric cells, which produced a current from the light coming from the star, and that was used to turn on a switch that would turn on the exhibition lights in 1933. So imagine it's so bright that it turned on a light in the exhibition of the World Fair in 1933. So
that's a wonderful fun fact. In 1933, that is, that's a little bit ago. So we'll go with, so it's 30, 70, something, 70-ish, ballpark years ago. And Arcturus is only 36.7 light years from the sun. So if that World Fair broadcast their results, of Arcturus turning on the light, that broadcast would actually have reached Arcturus. And actually, everything that we've broadcast would have reached Arcturus up to about 36.7 years ago. I just say I got the impression that there was a little bit of a color here. So the spectral type of Arcturus is a red giant, spectral type K1. I'm not sure if it's coming through too well on the Malin cam, but you can see that Connor and Laure have actually done some color adjustments to try to bring it out. This is what you would see if we could get you up to look through the eyepiece at the telescope. All right, now let's see here. What else do we have? It looks like Manny is in chat, actually. So very busy today, our speaker. Manny, do you want to tell us real quick how Arcturus can be used to find the M3 cluster? If you're still here.
The cluster like M3s actually can be spotted between the halfway point between the Arcturus and another star. I I lost the slide, but yeah, if you take the halfway point between Arcturus and the the Corcaroli star, you can see M3.
Oh, wonderful. That is a really, really good tip. So if you kind of hold up your hand to the sky, you can actually use your hand as kind of an angular measure. And you'll find that your pinky finger at arm's length should just about cover the moon. So if you wanted to go sort of halfway, you might want to stretch out your whole hand palm, sort of all fingers out. And that sort of halfway point should get you to M3, which you will then want to use binoculars or a telescope for, because it will, I think, be a little bit too hard to see detail. Now, you said, I believe M3 was just naked eye visible in a, let's see here.
Yeah, it is just barely visible with imperfect viewing conditions.
Excellent. All right. So let's go ahead and see what else we can get to. It looks like there's a bunch of different bright objects out tonight. So I'm going to say, Connor and Laura, can you please check what the height of the moon is? The moon is a little bit too low in the sky at the moment. That is too low. It's just rising. So let's go ahead and see if we can get to Vega. And now Vega is another nice and bright star, but it's a little bit different. Something a little bit, bright, but it's not a red giant. So let's see here. Looks like Connor and Laura have us on our way. And this is one of the favorite things about the 1 meter telescope. You'll know how fast it is when they move around. And Viva Las Vega, says June. I will go ahead and reiterate that. So hopefully we can get the dome rotated around so we can see Vega. And this is another nice and bright object. First coming through a bit high on counts, it looks like. But it seems to have auto adjusted okay. And Vega, yeah, we're just getting a little bit low on background. It is a fairly bright star, so we should be able to get a nice crisp image off of it. Now, Vega, being very bright, is also commonly used for navigation, and has been one of the sort of more famous stars in the sky. It's been given many names by many people over the years, but it's a really interesting star because after the sun, Vega is sometimes called the most important star in the sky. It actually used to be the North Pole star. So if I go ahead and I'm just going to steal Connor and Laura's screen again to go back to their big sky view, we now have a star at the pole called Polaris. And on this map, you can see that's the point where all the other stars appear to go around because of the rotation of the Earth. Excuse me, talk about audio problems. Now, in the past, that star appeared to shift position because the Earth's rotation has this wobble over not 5 years, not 25 years, but tens of thousands of years. So Vega was the North Pole, or was at the North Pole about 12,000 BC, and will be again in around the year 13,000. So we're now in the year Oh gosh, what year is it? 2021, I hope. And if you're willing to wait around until the year I don't know what we'll call it, 13,000-ish will probably be the year, 13,727, then Vega will be at the pole again. And so Polaris and Vega actually change positions as the pole star over time. So Polaris will not always be the pole star. At some point, we'll get this very, very, very bright star. And I don't know, I suppose celestial navigation will be a little bit easier. So, Arfa, it looks like you have some wonderful Vega facts. We want to go ahead?
Sure. So Vega is actually a younger star than our own sun, and it's just 450 million years old, but it may only live another 450 million years. And of course, everyone have seen Vega in the sky if they knowingly or unknowingly, because you don't need any special telescope or binoculars to view it. Also, there I have a few more facts. That is that it is actually relatively close to our sun. It's just 25 light years away, and it is the size. If we talk about its size, it's a massive star. It's twice as large as our own sun. Thank you.
Wonderful. That is a very good fact. And of course, that larger size is why they think it won't live so long. Um, and yeah, that is absolutely true. These bigger stars, they burn out quickly, as we have actually learned from Mani as well. Those open star clusters having lots of young stars, they tend to explode. The globular clusters having lots of old, smaller stars, they tend to last for a very, very long time. And of course, this is part of the summer triangle, as has been noted in chat. You have not just Vega, but Deneb and Altair will make up a summer triangle. So if you are out stargazing in the evening, you can look and see if you can still catch that summer triangle. So let's go ahead and see if we can make out possibly a binary next. I've been wondering if Algeba would be up. So if we can try to get a target, we'll see if we can catch the visual binary Algeba. I'm not sure if it's up high enough, but if we go to, our telescope will tell us. It looks like we might be able to catch it. Let's see here. So Algeba is a visual binary, which is a pretty fun one because we should be able to make out the two stars in the binary from the telescope if it's not too bright outside. So this is probably the last one we have time for tonight. We'll take any last suggestions in chat if you have them. The moon is too low. We already checked, so we won't be able to go to the moon tonight. Although I always encourage people to go to the moon whenever they can. It's very, very nice. And Algeba is, of course, over on the same side as the sun. So it will be a little bit harder to spot. Let's see if we can just get the binary. Oh, here it comes. Looks like Connor and Laura have done it again. So this is a binary star. We're just having a little trouble bringing out the detail. Let's see if we can fiddle with it a bit and get some detail on both of those stars. Now, binary stars are not super unusual, and we actually heard Manny talking about them earlier, but visual binaries are, because of course these stars are so far away, it's really, really hard to see the separation between them. They actually have to be quite far in order to actually detect them. Now we're just messing with the intensity here. You can see Connor and Laura trying to adjust it to bring out the stars. And maybe if we can get a little bit of a zoom on there, we might be able to get the light levels to behave. But Algeba is a double star that we can not naked eye make out, but with a telescope we can actually resolve the double, and it's been called one of the best double stars. And I won't go ahead and make any claims to best double stars. Alberio is also quite nice, but Algeba comes from Arabic, and it's a lovely binary system which has been slowly widening over time. So the orbital period is quite long. It's estimated to be between 5 and 6 centuries. So they're quite far away from each other. And it looks like Algeba A has an exoplanet. So that is pretty fun. I hadn't heard of that. I'm not sure if that's coming in from Connor or Lore. But exoplanets are always really nice. Let me see if I can just get a little more detail on Algeba here. So we're just going to go in and see if we can resolve those two stars. A little bit, yeah, it is just, we're getting a bit of interference from the sun. So it looks like it's a dim image, but what's actually happening is that there's a large background light level that the eyepiece camera is just having a little bit of difficulty resolving. So you can see that the image sort of bounces around. That's due to our atmosphere and the fact that we're using an eyepiece camera, which kind of shows you the light as it comes into the telescope. If we were to hold the shutter open and create exposures, you would actually see the stars as single objects. So let's see. I've just fiddling with it a little bit. I probably made it made it slightly worse. There we go. And just bringing out that double star system. I think everyone can see now that it is two stars. Now, when they split apart like that, that's the atmosphere of our planet bouncing around and making it a little bit difficult for the light to travel straight through. Oh, looks like we have a little bit of planet facts coming our way. So the exoplanet on Algeba A is about 2 Jupiter masses. That is really, really cool. 2 Jupiter masses would make quite a nice, it's almost a second star. So maybe almost a 3-star system having a planet that large. And it looks like that second Jupiter mass, 2 Jupiter mass planet on Algeba A is about 2 AU from its star, so twice as far as Earth and twice as massive as Jupiter. That is a really, really interesting, really interesting system. Of course, these stars are visually very, very striking. I'm not sure how much of the color is coming through, but you see that as the light kind of dances around here, you get this lovely, rich, sort of golden yellow color coming through. And the 2 stars are K and G type stars, respectively. So if you remember your stellar classes, I believe the classification is commonly phrased as oh boy, an F grade kills me. So O, B, A, F, K, M. That gets you your order for your stellar spectra from hottest to coolest. So a K star is quite hot. A G star would be more yellowy like our sun. And together they have a lovely sort of golden yellow kind of color. All right, so Algeba is very, very fun here. I think we could probably stay on this all night, but we do have a limited amount of time for this broadcast. So because we don't have too many more suggestions coming through and because we're almost out of time, I'm going to go ahead and get ready here to take back the screen, and we will go ahead and hand over shortly. So a huge thank you to Connor and to Lore, our telescope operators tonight. They have done a fabulous job with the dome and the telescope. All right, everyone, this has been very, very fun, but it's time to pass over to the outro. Tina, are you ready to go?
Yes, of course. Well, everyone, you have been listening to the York Observatory's weekly TeleTube broadcast, the Astronomy and Astrophysics program, written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been myself, of course, Arfa, Matt, and June. All of our programs are free. However, if you would like to make a donation or to buy one of our observatory astrophotography calendars, which are now 50% off on the York U Bookstore online site, then you can see our website at observatory.info.yorku.ca. As always, you can also connect with us on Twitter with the handle @York Observatory, and check out our website for show notes, content, updates, and contact info. Again, at observatory.info.yorku.ca. A special thank you to our speaker, Mani. Congratulations on finishing your excellent co-op and for teaching us about your project. Any questions from Mani or our team are welcome in the live chat. We'll be around for a little. And thanks for tuning in. Clear skies and have a great night.